Speaker is Sam Roberts from PsiQuantum, and he's going to be talking about modular decoding.
Cool. Thanks, Earl. Thanks very much to the organizers, and thanks for everyone for coming. So today I'll talk about modular decoding, which is about how to deal with the large-scale decoding problems that we'll unavoidably run into in real fault-tolerant quantum computing. So this work was done at PsiQuantum, and here's a picture of the architecture team when we almost had everyone together at one time in one place. You might notice some not so seamless photoshops. But special thanks, thanks to the whole team, because the whole team had contributions to the project, but special thanks go to Hector, Chris, Ye-Hua, Naomi, and Fernando. And there's a paper there if you want to check that out, or you can talk to anyone that's from the team that's here this week. There's a few of us. Okay, so the motivation for this work was quite simple, and that is, contrary to what you might have heard, fault tolerance with some of the leading approaches, such as the surface code, was not scalable. And the issue there is really that we didn't have decoders that meet the practical demands for real fault-tolerant quantum computing, and in particular, we didn't have decoders that were scalable, meaning they can keep up with the large amount of data that's being produced in a fault-tolerant quantum computation, even as we scale up that computation. Fortunately, this is not a problem anymore, and I'll talk to you about one such approach for solving this problem. And before everyone has their mid-morning nap, I just wanted to flash up the main results quickly. So the main contribution is really that we provide a kind of scalable and practical approach to decoding fault-tolerant computations based on topological codes, such as the surface code, everyone's favorite, or maybe not so much everyone's favorite anymore. Yeah, the main idea behind this approach is to really parallelize the problem in both space and time. So you can divide up the large problem into smaller chunks that you can solve in parallel. When you do this, we need to know that we don't lose any performance or that we don't lose any accuracy in the decoding. So we prove this modular decoding soundness theorem that guarantees that whichever way you choose to divide up the problem, you can always make sure it's fault tolerant and that there's no low weight errors that lead to a logical error. And then finally, to actually look at the performance in practice, we do some numerical studies with this approach, including on some relatively large-scale decoding problems and some ones of practical interest, like the 15-to-1 magic state distillation circuit. So they're the main results. And I also want to mention a bunch of related work on this problem. So I've seen a lot of focus over the last year or so. Of course, the original, the famous Dennis et al. Paper, it's always worth going back to that if you have a problem. It has a lot of elements of this in it. Same with the fusion-based quantum computation paper. There's some elements of modular decoding in there. And then there's some great papers from the Riverlane and Alibaba groups on this problem, and we have a couple of talks on that today. So it's a decoderful day. And okay, so now we can get into it. So for the rest of the talk, I'll just try and explain what these results are. And so to start with, let's take a step back and ask, what is the decoder? What do we want from the decoder? And what is the problem anyway? So we're confronted with a lot of scary numbers in fault tolerance. We have large qubit numbers, very low error rates that we need. But of course, another problem that's receiving a lot of interest lately is the enormous amount of classical data that you see. So if you look at a typical kind of surface code using a typical kind of clock speed, you might expect about a gigabit per second of data per logical qubit. And if you have hundreds or thousands of logical qubits, this can add up pretty quickly. And this data is really important. It's important for two reasons. One is that it contains information about the locations of errors, or the likely locations of errors. So we do these measurements redundantly, of course. And so we have checks, and then we can infer syndromes. And then based on that, we want to know where the locations of errors are. And then ultimately, what we really want out of the computation is a kind of error-corrected logical outcome for when we do logical measurements. So if you look at a typical quantum circuit, the part that we actually want to get out is the computational output. And so you can think of the decoder's job as providing these error-corrected logical outcomes. So it comes up with some recovery, and then you use that to infer what the correct output of the logical measurement is. And the point is that we need these logical outcomes in real time. We can't just wait till the end of the computation and then decode them, because we need them for adaptive logic, which happens everywhere in a quantum computation. One particular example where it happens a lot is if you're using magic state injection. So if you're achieving a universal gate set using magic state injection, then you need adaptive logic every single time you do a non-Clifford gate. Here's the example for the T gate. To perform T gate, you prepare some T state, you do a C naught, and then you measure out that magic state in the Z basis. And then depending on the outcome of that measurement, you then perform this conditional S gate. And in fault tolerance, that Z measurement is not just one single measurement. There's a whole bunch of physical measurements that go into that, and it's the decoder's job to come up with the error-corrected outcome. And a useful metric or a useful quantity is called the reaction time. It tells you, for a given operation, how long does it take to receive all of once you've done all the measurements comprising that operation, how long does it take to send those results to the decoder, and then the decoder to return the error-corrected or the decoded outcome, and then decide if you need to do that conditional gate or not. And the reason the reaction time is important is because it determines the logical clock speed. So if you have a slow reaction time, then you're limited at the rate at which you can perform logical gates. Here's an example on how you can see that. This is the problem of unitary synthesis. So you take a single qubit gate and you want to decompose it into some Cliffords and Ts. If you're performing these non-Clifford gates using a kind of generalized magic state injection circuit from the previous slide, you kind of just chain these together. The only difference now is instead of C naught, you have some Clifford conjugated C naught. So it's a Pauli controlled X gate. And this Pauli controlled gate depends on what the unitary you are trying to synthesize is, but it also depends on what the outcomes of the measurements preceding it were. So each time you want to basically, before you perform the next gate, you have to know the decoded outcome of the previous gate. And this can cause problems. If your decoder is too slow, so if it's not decoding the data at the rate it's being produced or faster than that, then you can run into what's known as the backlog problem, which was highlighted or identified by Terhal in this nice paper. And the idea is that while you're waiting for a decoder to return the output and you have to idle your gate, you're also producing more data. You're doing measurements to try and identify locations of errors. And then this can kind of cascade if your decoder is not decoding at a fast enough rate. And you end up with an exponential slowdown in terms of the number of T gates. So you lose all quantum computational advantage in this setting if your decoder is not fast enough. So this tells us that we need to parallelize the decoding problem, because as you scale up the size of the computation that you're doing, if you only had one decoding module that was processing all the data in serial, then you're eventually there's going to be a size at which you're producing data faster than you're decoding it. So we need parallelization to do scalable computation. And so here I just have the kind of summary of what we want out of a decoder. We want this low reaction time, so the outcomes are returned soon after the measurements are done. We want high throughput. To make sure that we have this low reaction time, we need to process data at the rate it's being produced, even as we scale up this computation to many logical qubits or many gates. And then, of course, we also want high accuracy. The performance of your scheme, as we all know, is very dependent on the decoder that you have. And so we propose modular decoding, which meets these requirements for when you're doing fault tolerance based on topological codes. And the idea is, as I said before, to divide up this global problem into smaller problems that can be solved using everyone's favorite standard offline decoding approach, such as a matcher or a union find or whatever your favorite is. Importantly, these problems aren't all independent. They need to communicate in some way. We need to make sure that these local corrections build up to give a globally consistent correction. But we want to make sure that those dependencies are kind of low so that we're not, if the dependencies are long, then we end up having a longer reaction time. So that's basically the idea at a high level. Now we can kind of go into a little bit more detail for the remaining 10 or 15 minutes. To understand, we should first understand what a decoding problem looks like before we talk about the modular, modular decoding, and to understand, to understand what a decoding problem looks like, we need to understand what a fault-tolerant quantum computation looks like. And the important thing here is that fault tolerance is not about, it's fundamentally not about codes, it's about protocols. And protocols live in space and time, and so we should think about them as space-time objects. This was a point nicely made in Nicola's talk. And there's many ways to think about space-time protocols. There's ZX calculus, there's tensor networks, there's quantum instrument networks, there's quantum circuits. There's also pictures like these where you kind of just draw where you want the boundaries of the service code to go in space and time. So the picture here is basically specifying abstractly the instructions that you want to do on a surface code, for instance, to do something like here. It's depicted as lattice surgery. There's many reasons to think about, or many advantages to think about operations in space-time. One is it lets you reason about the fault-tolerant properties of the protocol. And secondly, you can also compile more efficient operations. So one example of how to think about this is using the logical blocks picture, which Daniel talked about yesterday. And so the idea here is you can build up a general computation just by sticking together these elementary building blocks and just sticking them together in space-time. So here we have built up this lattice surgery computation using these two elementary building blocks, the GHZ block and the GHX block, which are kind of motivated by the ZX calculus. Here, the GHX block is just like the Hadamarded version of a GHZ tensor, and I can't take credit for that naming. That's due to Terry Rudolph, probably one of his finer contributions to science. But another advantage of thinking about computations in this picture is that it lets us compile down to different models, physical instructions on hardware for different models of computation. So, everyone has their own favorite way of thinking about computation. A few of them are listed here. There's circuit-based, where you kind of perform unitary gates and single qubit measurements, or maybe multiple qubit measurements on some static array of qubits. There's measurement-based quantum computation, where you prepare some kind of fixed large entangled resource state, and then the computation proceeds by just doing single qubit measurements, destructive single qubit measurements typically. And then there's also fusion-based quantum computation, which is what we think about at Psi. And the idea is you prepare resource states of a fixed size, independent of the computation, and then you perform destructive 2-qubit entangling measurements called fusions. They're just Bell basis measurements typically. And fusion-based quantum computation sits in this kind of nice Goldilocks zone here. It's useful for us because that matches our operational primitives, but it's also useful for thinking about modular architectures, but that's probably for another talk. Okay, so that's the quantum part. That's what a fault-tolerant quantum computation is at a very high level. What we see in the classical world is just all of the outcomes of all of these measurements that we've performed throughout the computation. And the important thing is that these classical outcomes just follow the same structure as the quantum computation. So it follows the same kind of geometry. This data is very important, as I already said, and it's our kind of window into the computation. There's two important properties. There are the checks, which are parity constraints on the, in the absence of error, there's certain parity constraints on the measurements because you're doing the measurements redundantly. And then when you see you see an outcome that you don't expect, that signals the location or the presence of some error. So examples of checks in the circuit-based picture is if you do some repeated measurement of a stabilizer, those two outcomes should agree, so that forms a check. Then there's related notions in fusion-based and measurement-based quantum computation where there's certain constraints on the outcomes of measurements. There's also the logical correlators, which I won't talk too much about, but the idea is that when you're doing a logical measurement, you just don't do a single physical measurement. It's made up of many physical measurements. And so the outcome, this logical outcome, will be, the mod 2 addition of a bunch of these outcomes in the absence of errors. We also have the notion of the fault distance, which says that, you're probably familiar with the code distance. Fault distance is just the same kind of idea, but for a protocol. It's the minimum number of errors according to whatever error model you have to flip a logical measurement outcome without leaving a syndrome. Okay, so decoder, I'm sure most people are familiar with this. Decoder takes a syndrome, it produces a correction, which is just an error that is consistent with the syndrome, and then using that correction, you can then update the outcome of some logical measurement. That's roughly the idea. And there's this important notion called soundness. So we say a decoder is sound if for any syndrome it returns a minimal weight correction that's consistent with it. And so this is a nice property to have because it means you can always correct up to d minus 1 over 2 errors for a fault distance of d. Because if you have such an error, then the weight of the correction will be less than that, and then the combined error plus recovery will be weight less than d, so no logical error can occur. This is not a necessary or sufficient condition for having a good decoder, but it's usually it's a good design principle for making sure that you're not missing any local errors that could cause problems. Okay, and then we can go through what modular decoding is fairly quickly, I think. So that's the decoding problem. How do we actually decode that? Well, rather than looking at this big picture, let's just look at a quick 2D example. So this is like a schematic representation. Vertices correspond to checks, and edges correspond to potential error locations. So what do errors look like in this picture? This one in the middle here, if you have a chain of errors, you'll see a syndrome on the boundary. If you have some closed loop of errors, it's either going to be benign, it's not going to hurt you, it's a trivial error if it's like this, or in this example, if it wrapped from top to bottom, then it would be a logical error. Okay, and then let's take a look at this particular error. How would we decode this? So if you're using like a sound decoder, like a matcher, it would just try and pair up these syndromes like this. It's not exactly the error configuration, but it doesn't matter because the combined error plus recovery is a trivial error. But now let's look at the modular case. So what would happen if you want to decode this problem in 2 steps? So you want to have 2 decoders that can decode this problem. Decoder 1 and decoder 2 responsible for the left-hand side and the right-hand side of this schematic. Decoder 1 will just see this single syndrome, and so it can match to the top. It can match to like a boundary, or it can match to this interface on the middle. The reason it can match to the interface, it's a choice you make, but it's a sensible choice because there could always be a syndrome just on the other side that you want to match with. And so decoder 1 will do the minimum weight thing it can do, which is match to this interface. Decoder 2 will see this updated syndrome just on the boundary there, and then it will then match like this. In this case, it worked fine. It was the same as the global, but it turns out there's actually some issues that can happen. So by just naively chopping up this decoding problem, you can reduce the effective fault distance. Meaning that there's errors of weight less than d over 2 that can cause a logical error. And the solution to this problem is to use buffering. And so a buffer is just an extra window of information beyond which the region that the decoder is tasked with correcting that it can use to make a more informed choice. So the decoder in this example is tasked with correcting this region on the left here. It also has access to this region in the middle here, but it won't return a correction for this. And then there's some other information that it doesn't have access to. And so in this example, what it will do is you can think about it as returning a correction on the combined commit plus buffer region, but then just restricting the correction to the commit region. And then that buffer region can be revised later on. So that's buffering. And that's basically what a decoding problem looks like. You divide it up into a bunch of smaller decoding problems, which we haven't talked about how to do that yet. But each of these problems is basically just specified by 4 regions. There's the commit region, which is what it's tasked with correcting. There's the past, which is some region that's already corrected by some previous decoder. And importantly, it doesn't have access to that whole past. It just has access to the updated information on the boundary. And then it has the buffer, this extra information. Then it also has the future, which is just some non-visible information, or maybe it's yet to be determined. You haven't decided what you're going to do there yet. And we have this buffer, this soundness theorem that I mentioned. The idea is that any way you decide to split it up, provided you use a sound decoder, so one that returns a minimal weight correction, and provided you also have a sufficiently large buffer, which in practice, we can talk about what that means, but choosing a width of the fault distance is sufficient, but you can get away with less in practice. So provided you have this soundness and a sufficiently large buffer, then the overall procedure is sound, meaning you can always correct up to d/2 errors. How do we divide into smaller blocks or into these subdecoding problems? There's many ways that you can do this. The only real causal constraint is that neighboring commit regions cannot be decoded in parallel because they have to agree on the boundary, so you have to make sure they're consistent, that you're not introducing syndromes on this boundary region. So neighboring commits can't be decoded in parallel. And then with that, you basically just want to try and minimize the reaction time. So the reaction time depends on the depth of dependencies, the number of decoders that need to communicate in a chain, and also it depends on the size of the buffer and commit, because that determines how long it will take to decode each problem. One solution to this is to use edge and vertex decoding, where the idea is to basically take the structure of the decoding problem, the structure of the way we stuck the blocks together to determine how to decompose into subdecoding problems. There's 2 types of tasks. There's edge tasks and there's vertex tasks. The edge tasks are just all these 2D slivers between the blocks. So when you stick 2 blocks together, that defines an edge task. It's a 2D region. And then that's the where you have to do the correction on this 2D region, but it also has the buffer that's just some region around it. Once you do these edge tasks, which can all be done in parallel because they're not neighboring, you then do the vertex tasks. So you're basically fixing the boundary conditions on all of these blocks, and then you can just decode them. And they can also all be done in parallel because they're all separated by a thin 2D sliver. So this is nice because the decoding tasks are small, and also there's only 1 round of communication between them. So this is the lowest reaction time that we could think of. Numerically, I'll wrap up now. I'll just quickly say that in practice it performs well, so you can benchmark it on just like a simple thing like a long identity block, like d by d by 5d, and divide that into 5 blocks. This is the plot of logical error rate as a function of buffer size for a bunch of different distances. These horizontal lines are what you would get if you decoded it without parallelization, just all in one go. And so you approach that as the buffer size increases. And in practice, you see you don't need a buffer of equal to the distance. You can get away with maybe d/2. Also, there's the more complicated example. I won't talk about this, but there's a big circuit for the 15:1 distillation circuit. And you can decode this. You see buffering is necessary. If you don't have a buffer, the logical error rate doesn't go down as you increase the distance. But if you have a sufficient buffer, it does. So it works well in practice. And so with that, I'll wrap up. So we have modular decoding meets these conditions. And there's a bunch of other directions that you could take this. A couple that I would mention, or I'll just mention one. The idea is that it opens the door to using these kind of non-efficient decoders like tensor network decoders, because the complexity is linearized after the distance, so you only need to worry about decoding a d by d by d block roughly. But there's a nice paper by Delphos and collaborators on this trade-off. As your decoder is slower, you will, in practice, then need to delay a bit, and this can introduce more volume and more errors. But so there's a trade-off there, but you can kind of optimize for that. So with that, thanks.
Thanks for the very nice talk. You mentioned on the last slide the possibility to also extend this to LDPC codes, and it seems like it should just directly work. Are there any subtleties that you're aware of when you try to apply?
Yeah, thanks for the question. So I don't know. I'm not claiming that we can directly extend it to LDPC codes. Then there are some parallelized decoders for certain classes of LDPC codes. There might be some lessons there. Some potential pitfalls that you might imagine is that LDPC codes with nice properties typically have high amounts of expansion. And if you're going to buffer, so you choose some commit region, then you try to buffer, that buffer might grow very quickly. And so the individual decoding problems might get quite large. So just naively applying it might not work. I mean, you could decode it, but it might not lead to any speed advantage. So.
Hi, thank you. Do you know why it is that you don't need a buffer size that's the full code distance?
Yeah, good question. I guess it's a question of worst case versus typical case for an error model. So worst case, you would need, if you want to correct up to D on 2 errors, you need this full buffer size of D. But in practice, a typical error that you'll see is actually, it's going to be weight, proportional to the volume of your lattice. So it's going to be much greater than D. But maybe a bunch of those are not so, yeah. So it's about typical versus worst case, I think. But I don't know, something about the structure, but I don't know exactly what that is, yeah.
I've got a natural question that slips in just there. Did you actually look at any of the smaller size windows that would maybe be better in practice? Do you have numerics on them?
So the smaller windows, you mean like something like this, where like if we use like a buffer size of like 4, you can see that you're quite a ways off doing the global approach. So it seems like here you probably want to be around the D over 2 or maybe a bit larger. But there's also it's the classic trade-off of speed versus accuracy. So something to optimize for, but we haven't optimized for it.
Does the frequency of decoding between blocks matter, or do you always want to decode all of the blocks as fast as possible?
The frequency.
Yeah, can I read it?
Frequency of decoding between blocks matter. I'm not sure exactly what it means, but fundamentally, it doesn't matter if you're just worried about the backlog problem, then the decoder speed doesn't matter because you'll never run into the backlog problem if you're parallelizing. But in practice, the decoder speed does matter for the reasons basically talked about in Nicola's paper. Because you don't want to be waiting around. If you're waiting on the decoder, you're still waiting around. You're idling your computation. It slows down a little bit. You can slow down the overall computation, and you can also introduce more errors in doing so. So you still want fast decoders, but it's just that the backlog problem won't matter. If that answers the question.
Hi. So maybe I'm just like reading the graph wrong or something, but it actually looks like it reaches the global decoder like at a constant buffer size for like all the distances reach it at the same, right? Like the D equals 13 is reaching it pretty much at like 10 or 11, which is like pretty much 13. And then the 19 is like about the same.
Yeah, it looks fairly similar. I think, probably need a bit more resolution to really say for sure, but I think it does look like, you do need a larger buffer, but these are, the difference between 13 and 19 is also not so large.
Yeah, okay.
In this example, you see if you have like a very small buffer, the logical error rate is just flat as you increase the distance. And then, if you have a buffer of, what's this, 8, you do start to see at some distance the logical error rate actually lifts up. So you should need a different, the buffer size should depend on the distance. It's just,
Okay.
I'm not sure exactly what function. Some proportion
Okay,
makes sense in practice.
thanks.
Okay, it's time for the break now, so should we all thank Sam again? So we're back at 10:45 with more decoding talk.